So calculation of force law. So basically we all know that entropy by definition is equals to U plus PV. U is the internal energy of the system, PV is pressure and volume. And we know entropy, which is ds by definition, is equals to dq reversible over T. Right? Now, pretty much these two formulas you have to memorize, especially this formula. Why? I'll tell you in a while. In another case, we have du is equals to cv dt. These only applies in two cases. One, constant volume, which as a current process, we have du is equals to cv dt. And two, in a perfect gas, cv, not du, is equals to cv dt. So these are the two cases where d equals to cv dt. So for perfect gas change of states, we have a ds equals to dq reversible over T. Now, to find check delta S, which is change the S, we have to multiply this formula. Now we know that du is equals to dq plus dw, right? Now I want to find delta S. We can write delta S is equals to integral of dq reversible over T. Now we have to find dq reversible. Since we know d equals to dq plus dw, we can manipulate this. So you have dq reversible is equals to du minus dw reversible. Now dw reversible is equals to minus p dv, and du is equals to cv dt. Why? Because we're doing the perfect gas versus with change of state. So we could write dq reversible is equals to cv dt minus p dv. Minus, that's minus, it's positive. So we could replace dq reversible as cv dt plus p dv. So now I have delta S is equals to cv dt over T plus p dv. Now we can split this integral into two parts because this is sum of the integral. So we can write delta S is equals to the integral of cv over T dt. Now cv changes with temperature, so we can put this over here. Meaning temperature is constant, cv is equal to 0. Plus integral of p over T dv. Now p over T we can replace with as a nr over v, because pv is equals to nRT. So p over T is equals to nr over v. Alright? So now I have delta S equals to cv T dt plus nr 1 over v dv. Now why did I pull out nr? Nr is a constant, so that's why I put it out. Alright? So now I have this is equals to ln v2 over v1. So delta S is equals to C CB dt over T plus NR ln V2 over V1. That's it. So for pure substances, molar heat capacity CPM at constant pressure and constant volume. So you have CPM is equals to CP over mole, right? And CVM equals to CB over mole. Now this only apply for perfect gas. And like I said, CPM and CVM depend on temperature change. So if temperature is constant, like I said, du equals to CV dt, and dH is equals to CP dt. These formulas only apply for perfect gas, and the changes only when temperature changes. So in isothermal process, du and dH both equal to 0 because they only depends on temperature change. So for reversible isothermal process in a perfect gas, so we have Cp minus Cv equals to NR, I believe so, and CPM minus CVM is equals to R. CPM minus CVM is equals to R. Alright, this formula only applies for perfect gas. That's a reversible isothermal process in a perfect gas. So you pretty much have to memorize this formula to understand how to calculate. So at constant volume, you can write CV equals to dQV over T, which is equals to U T over V at constant volume, because du is equals to CV dt. This dQV is that's the heat capacity at constant volume. So it's something as du equals CV dt. So Cp is equals to the heat capacity at constant pressure or the pressure per dP. So basically this is pressure entropy, and this is our Cp dt at constant pressure. So pretty much I have to just memorize these formulas, and that's it. And so that applies for perfect gas, reversible isothermal perfect gas. So in the thermodynamics, change of state does not mean solid, liquid, or gas of a spoiled system. So change the U of a perfect gas, any change of state only depend on temperature change. So we have du plus Cv dt, and changing U equals to Cv dt. Now we can calculate Q, which is the heat, from Cp, because Cp depends on temperature change. And we can also calculate delta H, because delta H is equals to Cp dt. And Cp, like I said, this at constant pressure. pretty much delta U is equals to Q plus W delta H is equals to dt, and also delta U is equals to CV dt. Is our constant volume or in a perfect gas. So pretty much remember this formula and you'll be okay. So since delta U and delta H are both equal to 0 for a reversible isothermal process in a perfect gas, so you have delta U is equals to Q plus W. So you have W is equals to minus Q. So how do we calculate this? Now remember earlier we had dW reversible is equals to minus P dV. So we're going to use this formula and manipulate this formula to calculate W and Q. So how can we do that? So we can write W is equals to minus P dV. Sorry. So P, so we can write PV equals to nRT. Now P is equals to nRT over V. So we can replace P as nRT over V. So we have W is equals to minus nRT over V dV. So we can take this out because, like I said, isothermal temperature is constant and error are constant. So we can pull out all the constants. So we have a W is equals to minus Q equals to minus nRT and 1 over V dV is equals to ln V2 over V1. So this is our formula that we use to calculate W and Q for a reversible isothermal process in a perfect gas. And also this is also equals to nRT ln of P1 over P2. So we just replace that. This should be P2 or P1. This is when constant, okay, right. So we also write ln of P2 or P1. So we just replace that with this, depending on what we're given. So this is for reversible isothermal process in a perfect gas. This is how we calculate work. So pretty much that's how you calculate work and heat for a reversible isothermal process in a perfect gas. Always remember du equals to CV dt for two cases. When volume is constant, which is isochloric process, or in a perfect gas, d equals to CV dt. And also in a perfect gas, dH equals to CP dt. So just remember that and then you'll be good.